Recording.
Okay. So my name is Martin Kroom from Greenwaves Technologies. I'm Vice President of Marketing for Greenwaves. We've been doing some work recently on ONNX, supporting our toolchain, and I wanted to highlight our experiences, good and bad, with doing that. Greenwaves is a company making a processor, so we're a fabless semiconductor company. We're making processors that specialized in doing AI and DSP on extremely energy constrained devices in markets like hearables, IoT sensors, IoT devices, medical devices, and so on. Our first product is actually shipping, was production qualified at the beginning of last year, so we have customers actually using this and seriously and putting it into products. Part of the way that we actually control energy on GAP, one of the ways that we control energy on GAP is to actually use a strategy to move data across the chip in a way that's predetermined at compile time. So we don't actually use data caches inside the chip. And the reason for that is that data caches tend to be extremely inefficient on stream workloads. You probably get about a 30% cache hit ratio, which means that 70% of your loads are being thrown away, which is a lot of energy being used up for no particularly good reason. So what we do is we use software tools, and particularly a tool that we call the autotiler, which is essentially a memory planning tool. It's a tool that takes a model of the operations that need to be done and produces, in fact, searches for an optimal memory movement across a memory hierarchy, whether that be external memory to the chip or internal L2 or L1 memory. Inside the chip, we also have a compute cluster, which is multi-core compute cluster. In the GAP8 product, that's 8 cores with a shared memory architecture. So really, the most important thing for us to do is bring data in and hide all of that data movement behind computation on the cluster and keep the cluster busy. To do that, basically, we have a complete flow as part of that flow. And one of the things that the autotiler takes in essentially is quite a high-level model of the kernels that need to be executed. And then we have implemented specific kernels for the operations. So we heavily use fused kernel operations, which are handcrafted to really get the maximum energy efficiency out of the platform. We then have a tool called NN tool, which can suck in a TF Lite and now an ONNX graph and produces that model. Essentially, it's a lowering tool that's lowering the representation in TensorFlow Lite or ONNX onto the kernels that we've implemented inside. I wanted to give some background so you understand some of the comments that I'm going to make afterwards. GAP8, which is our first product, only operates on fixed points, so quantization is extremely important to us. And NN tool can handle those quantization steps with various different strategies inside it, or it can suck in quantization information, currently only from TensorFlow Lite, and then use that those tensor statistics and some indications of the quantization which TensorFlow has applied to apply quantization that's compatible with our kernels. So the experience with ONNX. So really what's gone very well and what I really appreciate with ONNX, particularly versus TensorFlow Lite, is a really understandable operator set and structure. There's fairly little duplication of operators doing more or less the same thing in a different way. There's great documentation. The operators are really, really well documented, and that's really, really appreciated by anyone doing development work with it. There's also a great operator versioning system. So when you update your operators, the versioning system is really appreciated. It allows us to import with confidence across multiple different versions, which is a difficult thing to handle. There are two areas that I really wanted to say that I think there could be improvement on. The first is quantization, and the second is something I called fusion friendliness. And I'll come to that in a following slide, but let's deal with quantization first. So at the moment, it seems like in ONNX, there's a mix of some fake quantization operators, some scaled quantization operators. And then there's a few more complex operators like a convolution, I think, and perhaps a linear layer where there's actually a specific quantized implementation of that kernel. And I'm really wondering what's the goal here. Is it to express a quantized graph, ONNX graph directly and then run that, or is it to provide the necessary information for a backend to provide its own quantization scheme for the graph, or essentially lower onto its own quantization scheme, whatever that might be? I mean, if it's expressing a quantized graph directly so that you can run it in its form in ONNX, that seems like a really open-ended subject, because you're going to provide quantized operators for every single scheme with every single different quantization technique. You know, are you going to start support sub-byte quantization, variable bit width quantization? How are you going to support tensor compression? There's loads of things which really map close to the hardware as well, that have really direct effect in terms of performance on hardware. And I would prefer that you were concentrating on the latter, or at least that was something which you considered strongly. And if the latter is something that you consider strongly, then more information is needed than currently that's there. We obviously have, parameter statistics because we have the parameters, but activation statistics we don't have. And TensorFlow Lite currently, with all the tensors that are actually brought in a quantized graph, gives you at least minimum maximum information on every single tensor. It would be really nice to get standard deviation and mean information, and that with that we would be very happy and would be able to do quite a bit we'd be able to map onto our existing quantized operators. It would be nice to have some more statistics, particularly having the min-max, standard deviation and mean by channel, and also potentially adding some outlier statistics in terms of weak and strong outliers. Those would help us do a better job in terms of the quantization. And so my suggestion is that you add a statistics metadata to every tensor. Well, you could do it just for the non-constants, but I mean, in a sense, if you're going to do this in, why not do it in a sort of homogeneous manner and just do it for all the tensors, even though it's somewhat redundant on constants, I agree. Anyway, we would be happy to participate in any effort to do that. The second area I'd like to cover is what I called fusion friendliness. There's one thing which is kind of a big problem for us, which is that we have optimized fused kernels. And it's very difficult to get to highly optimized fused kernels from elementary operators. It's always use a kind of, it's a little bit unfriendly way of describing it, but I always kind of describe it like moving from a cow to mincemeat. It's very difficult to get, very easy to go one way and difficult to go the other way. So you do have some fused operators. For example, you have a GRU operator, which is great because TensorFlow Lite doesn't have it. But there seems to be a move towards functions containing subgraphs of, being composed of subgraphs of operators for a lot of the fused operators. That's fine as long as we know what they are. And I think the solution would be to encourage, or in some way make it kind of the nicest thing to do. I said force, maybe a little word, but really encourage the exporter writers to wrap any native high-level operators in the platform that they're exporting from in perhaps a function, and then with a function namespace, function name that somehow indicates to us where did that come from, what was it before it got turned into this subgraph. This would allow us to choose to say, okay, we have a good fused version of that operator, we can map straight onto that. Let's not look at the subgraph. Or if we decide, hey, well, we don't know how to handle that, then go into the subgraph and start lowering inside that subgraph. So those are the 2 points that I really wanted to make. And with both of those points implemented, I think ONNX would be definitely the best solution for graph export available at the moment. Thank you.